Hello everyone. This is Sumit. So I'll be talking about Slayer for Lowy. So just a quick background: Slayer is a way to configure deep spiking neural networks for Lowy. And so this in this talk, this is the outline. So I'll quickly go through the frameworks for computing with spikes, some theoretical stuff. Then I'll describe the Slayer tools that are available for Lowy, some comparisons. Then I'll run through the demos. So demos are going to be two parts. The training parts are publicly available, and I'll just go a quick walkthrough on them because the training will take some time. Then I'll do a live inferencing demo of those networks on the Lowy side. And then we'll run through the benchmark results, and that's it for today. So as you already know, Lowy is all about computing with spikes, and Slayer is a tool for configuring deep spike neural networks in Lowy. And with Slayer, you could possibly configure a deep spiking neural network that would do different kind of object recognition, or here in this example, I hope the video is playing, but here you should be seeing continuous action recognition being done in form of a spiking neural network. A quick introduction to Slayer. Slayer is a spike-based backpropagation method, and it has custom PyTorch implementation, and it's a discrete in time-based learning rule. And with Slayer, we have the ability to learn synaptic weights. That's quite normal, and we can also learn axonal delays, which is quite unique to Slayer. A quick background on computing in Spike. Why we would want to use Spike as a computational unit. So it's more about borrowing computing principles from biology. With spikes, we can get sparse communication with events. And with these spiking neural networks, we get massively parallel architecture that are doing spatiotemporal interaction, quite similar to what happens in real biology. And with individual spiking neural networks, we have this idea of local compute and massive parallel interconnection. And this all results in low energy systems, which is the end goal for the systems, right? That's the inspiration from biology behind the spiking neural networks. So as we already know, biology uses spikes, and spikes are very sparse spatiotemporal patterns. So these are events in time. Generally, the magnitude is less relevant rather than the time where the spike is necessary. And it's the general idea of spike only when necessary, or when you have enough information to communicate between the sample. And the fundamental computational unit of a spiking neural network is a spiking neuron. So they can be thought of a mathematical model of biological neurons, and they have the property of taking in input spikes, and they will respond in terms of spikes. So the input and output of our system are always in the form of spikes. And I guess most of the people are already familiar with spikes, but people with deep learning background, we can think of spiking neuron more like a different kind of activation function, which has some kind of temporal component, which we'll see here. I hope you guys are seeing the laser pointer. So, overview of the temporal interaction that happens in a spiking neuron. So whenever, as I already said, a spiking neuron takes a spike as input, and whenever the spike comes through synapse, based on the synaptic weights, we get some kind of a temporal response. These are called synaptic potentials. And as many input spikes arrive across different times, we have the postsynaptic potential can be either increasing or decreasing based on the synaptic weights. And all these synaptic interactions accumulate over time, and the resulting voltage is usually called a membrane potential. Usually in spiking neuron, we have a notion of threshold, and whenever these membrane potential crosses the threshold, the neuron responds with its own output spike, and that is called spike. And immediately after the spikes, the neuron tries to reduce the spiking activity by lowering membrane potential. That phase is called the refractory phase of the spiking neuron. And this is in general how spiking neuron works. There can be there are many different models for spiking neurons, but overall, they demonstrate this kind of temporal dynamic behavior. And what is a spiking neural network? Is you just replace the standard activation function with spiking neuron, and basically we have spiking neural networks. Since spiking neurons takes input spike and provides output spikes, a spiking neural network takes a bunch of stream of input spike and output spike, communicating, producing output continuously in time. So there is a notion of continuous liveliness in spiking neural network that is quite different than standard neural networks. And with this kind of architectures, we can achieve sparse, local, parallel, and spatiotemporal behavior in the system. So that was a very quick overview of why you would want to get spikes and what are spiking neural networks. So coming back to Slayer, Slayer is a tool for training deep spiking neural networks, and the way it works is we directly consider the exact spike times instead of the spike rates. So that's a key difference than most generally available training tools. And there are two fundamental principles for training in Slayer. The first one is temporal error credit assignment. As we saw in this spiking neural dynamics, whenever a spike arrives, it will create this kind of a temporal dynamic response called postsynaptic potential. And when we try to do back propagation, what essentially this means is you need to rewind actions in history. Essentially, when we have an error at a certain point of time, you will have to do the same kind of temporal error assignment, but in the reverse time direction. And that is one of the major principles behind Slayer. And internally, this is done very efficiently, so it's not that big of an overhead. Next, key principle is the notion of spike function derivative. As you might have already guessed, that spikes are just binary events in time. So, but when you want to do back propagation, you need to somehow calculate the derivative of this spiking mechanism, and that is mathematically not well formulated. So basically, it's a general idea of having a proxy functions for spikes. So how do you calculate the derivative? Is you have to look at the activity beneath the threshold to gain more information. For example, if you wanted spike at next spike apart from this one, then you can look at the membrane potential, and this is probably the point where you are going to get next spike. So when you look at the subthreshold activity of the membrane potential, that is going to give better cue on where the next spike is going to be, or where do you have to eliminate the spikes. And this can be done with relaxed versions of a relaxed function of spike threshold functions. In Slayer, we use more biologically inspired spike escape rate function, which is this blue curve. That's the double exponential curve, which is basically a probability density estimation of probabilistic spiking neural network spiking based on its membrane potential. But other kinds of relaxations are also possible, which in general fall under the category of surrogate gradient functions. And that was a very quick overview of the fundamental theoretical aspect of Slayer. But Slayer, we already have a PyTorch tool that is publicly available, and quick introduction of this tool. So Slayer PyTorch is designed so that we have Lego-like computational block that, when aligned together, will form a spiking neural network. So we have individual blocks for spike response, synaptic weight accumulation, spiking mechanism, and delays in the system. And when you combine all this system, you can actually model a spiking neural network model like as defined here. So this is a formal definition of a spike response model. And what happens under the hood is it is fully AutoCAD compatible. So when you link all these individual blocks, AutoCAD pipeline is already established, and That's how the gradients are calculated. And with the gradients, we also support, in the synaptic weights, we support dense convolution pooling as well as transpose pooling and unpooling operations. So we kind of cover most of the synaptic operation benchmarks. In addition, as we already saw, we support axonal delay in the system. And once these autograd pipelines are connected backwards, Slayer can learn the PSP response, the weights of the synapses, as well as the axonal delays in the system. And so that's a very broad level overview of how Slayer PyTorch works. And in general, Slayer PyTorch, it works for spike response model, but we have close integration for Loihi based on Cuba current-based leak integrated fire model that's in Loihi. And what that enables us is when you train a model with Slayer Loihi, we can have one-to-one mapping to the Loihi hardware. And this is kind of how it works. Basically, this is a representation of single layer in Loihi. So whenever spikes come in, it goes through the synaptic weight interaction process, and that synaptic weight then goes to the Cuba LF model inside the Loihi hardware. And after the neuron spikes, it has this axonal delay component, and the output spike is fed to the next layer. And how we achieve this close resemblance with the Loihi hardware is we kind of model all these individual blocks very closely. As we know that Loihi hardware, we can only have quantized parameters. So we use this notion of shadow parameters, which are floating point weights, which are needed for back propagation. And these are quantized on the fly. So we use this notion of shadow parameters, and all these models are modeled one-to-one. So that's basically a functional Loihi simulator in built-in Slayer. And with the back AutoGrad pipeline already built in, we have the capability of calculating all the gradients backwards, and these gradients are updated the shadow parameters, and the quantized parameters are calculated on the fly. So this is how Slayer for Loihi works internally. In addition to that, we also have Slayer auto modules, which help in easy network creation for training in PyTorch and executing in Loihi. So it has two separate components on the training side. So the intention of this model is to have very low barrier for training deep spiking neural networks with Slayer and mapping them to the Loihi hardware. So quick run through of how the system works. So basically, a user needs to describe the network architecture they want to use and supply a dataset module to you that is going to generate different samples for training and testing. And based on this, we have Slayer auto modules that will transform this network distributor to a Slayer network architecture, and the auto module also wrap the dataset so that dataset and wrap everything for PyTorch training. So this all happens automatically for training once we have the network descriptor and the dataset. Once the training is done, this happens in GPU space, and Slayer auto modules take care of most of the training components. And once the training is done, the training network is exported as an independent file. So it's generally a SDF5 network descriptor. And what we can also do is we can take this SDF5 network descriptor, and on the NX SDK slide, that's the Loihi SDK modules, SDK apps. We can also create the network on Loihi, and based on that, we can also wrap the dataset and execute the models on Loihi, and all this can be done in a seamless manner. And once the network is executed, the results can be supplied to the user. So basically, what Slayer auto module does is user will only need to describe the network, create the dataset that can be used, and Slayer auto module will take care of training on the GPU half. And once you have the model, the user will need to supply that to this NX Layer module, and the execution in Loihi is automatically taken care of. So that simplifies or lowers the barrier for training and executing deep neural networks in low-E. Finally, quick note of the capabilities that can be done, things that can be done with Slayer. So as we know, it's a spike-based backpropagation method. So with Slayer, we can do precise spike to spike translation or in temporal manner like this. So on the left is then random input strikes, and with Slayer, we can learn a network to transform these random input strikes to this much correlated spatiotemporal pattern. Also, as we already saw in the initial examples as well, we can directly process spatiotemporal data coming from DBS sensors or even just cochlea sensors, and so that are already in event form. Generally, the non-event data needs to be converted into spikes, but we do have some support for that as well. Slayer, with Slayer, we can learn synaptic weights and axonal delays, and with close integration with low-E, we can do one-to-one mapping of the network trained with Slayer to the low-E hardware. And on the spike encoding from, we can also perform end-to-end spike encoding in the process using some form of generalized linear model, and that can be fed to the spiking neural network and processed. And this whole system can be in an end-to-end manner. One thing to note is since Slayer is discrete in time-based system, so it actually interacts in a spike level manner. So this is not well suited for red quadrant models such as image classification, although you can do it, but probably it's not the best tool probably for red quadrant models. Where it's more suited is more the data that is more spatiotemporally active. If you have any questions, just pop them in. Otherwise, we'll switch to notebook demo. Are you seeing the screen now? The notebooks?
Yes, we can see it.
Okay, yeah. So I'll go through 3 notebooks, 2 for training the networks on GPU side. So these are already publicly available in Slayer PyTorch repository. So there are a bunch of examples, but these examples are specific to low-E. I'll quickly run through it because it's not possible to go through like multiple iterations of GPU cycles real time, but essentially we will start with, as usual, load all the required modules. Slayer modules reside, it can be imported as SNN, and it has like internal components like low-E parameters. These are low-E model is specific to low-E, so that's what we use if you want to train model for low-E. And the network configuration is usually described in the form of YAML file or in form of standard Python dictionary, which I'll show in the next notebook. Essentially, you define the number of time steps the network is going to run, the models parameters for the neuron models, and some training and testing parameters. And from this model, you can have a dictionary of all the parameters that are there, which can be used to load the model. And it's just this example is for NMNIST, but we are not doing the full NMNIST, but we are doing a subset of NMNIST using 1,000 samples for training and 100 samples for testing. And this is the standard definition that's in general for PyTorch. The only thing is the tensor that's returned is usually a 4-dimensional tensor, where the last dimension is usually the time aspect for spiking neurons. And this is the simple network definition. We have 2 fully connected networks taking 34 by 2 samples, 1 hidden layer with 5 tail neurons, and the next layer has 10 output neurons. And essentially in the forward, what we do fully connected interaction of the input, followed by the spiking mechanism for Loihi, and these are passed to the next fully connected layer and followed by spiking mechanism. That's essentially your output. In between, you'll see this delay shift mechanism that is to simulate a delay of one-time shifts that is needed to route the spikes from one layer to another. And that's essentially your network. Apart from that, these are standard PyTorch methods for creating the dataset and data loader modules, optimizer, and error modules. And these are some of the sample examples. You can see the images. So these are static at the moment, but it's usually a moving image for lasting around 300 milliseconds. And essentially, you train the network. That's as everything fits very well into this PyTorch pipeline. So if you're familiar with PyTorch, this all should be very familiar to you. And essentially, when you look at multiple epochs, you'll see the loss going down and then the accuracy going up, as you can see in the plots here as well. So this is an example of training the NMNS results in using Slayer Loihi. But as you could see, there are lots of manual and repetitive tasks, and that's what Slayer Auto is for. So in this module, we are trying to train the same network, but auto models take care of most of the redundant tasks. So the same network could be described in the form of dictionary like this. So essentially, you have the neuron parameters. The layer description is a simple list of dictionaries. So we just describe the input layer, the hidden layers, and the output layer. The dataset definition is quite general. It just needs to supply the event and Slayer dataset model will wrap it around to create a Slayer compatible dataset. And essentially, what's different is you can create these assistant modules, and that will take care of training. So once you create this assistant module, and once you wrap your network with Slayer Auto Loihi model, it will create the network. It will list all the description of the network, and training is as easy as you look around the book and you just call assistant.train and assistant.test, and that will essentially train your network. It takes care of all the redundant steps during the training process. And here as well, you'll see the loss decreasing and the accuracy increasing along the way. So that was that for training Slayer networks for Loihi with Slayer. So once you have the modules, you can export the model in the form of SDF5 model, and these models can be run on the NXSTK side. So this is the NXSTK module. Let me try run it. It's running. So as usual, we just import the NXSTK module. So that is a Slayer module. We're importing it as NX layer. And it also has auto modules which take care of all the different aspects for training. And this is the same dataset class that we had in the NMNS auto training model. Okay, anyway. And here we're just trying to inference 1,000 different samples for the purpose of speed for this live demo. And we can wrap around the same dataset model that we had before using dataset wrapper for NXLayer Auto, and we can also create the network by simply passing the encapsulated network that was generated after training. And executing is as simple as net.compile and net.setupio, and it takes care of everything. It's already running. So essentially, it will describe the network, how many cores it utilizes. So this particular network utilizes 17 cores, and this is the kind of distribution in different layers. And this ran on the board. So it's running super real time, meaning that 451 seconds of worth of data was processed in 12.72 seconds. And this is the accuracy for 1,000 samples. So slow auto models essentially simplify the network execution as just wrapping the dataset, initializing the network, compiling it, setting up input IO, and running the network. And that's how you get the results. So hopefully that's lowers the barrier for training. Trying to get back to presentations now. That was training and executing deep networks using SLAIR. So here in this demo, I just showed fully connected networks, but we can do deep convolution networks as well as include delays, axonal delays in the net system as well, and everything is taken care of seamlessly. So now I move to some of the benchmark results that we have to show. Okay, yeah, so this is essentially the NMS data that I showed you in the notebook. So it's actually moving. It's a 300 millisecond sample, and we're able to train a convolution architecture with conv architecture and fully connected three convolution architecture and a fully connected architecture as shown here. And even with the quantized parameters of LOE, we're able to get quite good performance up to 99.3. So that's pretty much competitive with the state-of-the-art unconstrained spiking neural network model with an order of less free parameters for training. So that's quite remarkable. And we can also see that SLAIR also results in quantized weights, which are much well within the 8-bit limit of the LOE hardware. And this network essentially finally used 37 cores, resulting in an energy delay product of 60.54 microjoule seconds per sample. And this was running for 300 time ticks. So similarly, we also have some results to show on anti-disease. So this is neuromorphic form of TI-disease dataset converted using silicon cochlea. So we essentially trained a simple fully connected network with 2 hidden layers, and we're able to get around 77%. So that is quite low compared to the other SNN implementations and even recurrent standard ANN implementations. But with SLAIR, we can learn axonal delays, and the LOE hardware also support that. So when you end up using these axonal delay features, we can have big significant jump in the accuracy with modest increase in parameters, and that kind of shows the power of axonal delays in terms of increasing the expressibility of the network. And audios are more temporally correlated inputs, so axonal delay here really help training. And so the weight distribution are kind of similar as NMNIS, but to note is in LOE hardware, we allow only a limited amount of delay to the system. That's why we see a bunch of delays that without concern would have gone well over the limit, but these are kept at the maximum ranges. And then this tiny network just uses 6 cores, and it's able to detect digit utterances, and it's running 33 times faster than real time with an energy delay product of around 50 microjoules per second, microjoule seconds per sample. Sorry. And DVSS has been one of our benchmark applications. So we're able to train, again, convolution architectures to recognize this Shrestha. And we actually trained 2 different versions of this network, one for resource constraints, and with that, that's a smaller network that is more aware of the resource constraints in the hardware, and that with that we're able to get around 96%. So that's pretty good, better than other implementation for DVSS, and what we also did was, and this network just consumes 18 cores, but what we are also able to train is a full-fledged DVSS network, and with that, we could get very close to 98% accuracy, but the number of, as you could see, number of low-E cores increased from 18 to 79. That's a significant jump in resources, but you get bump in performance as well. And these networks are running almost 10 to 15 times faster than real time. So, and we measure the energy delay product around 1,000 microjoule seconds per sample for the DVSS classification tasks. And we're able to map these DVSS network to our USB form factor Louis chip called Kabobe and run it in real time as well. And this is a video of the system running in real time, classifying the gestures as the gestures are performed. And this is an analysis of how the inference confidence increases over time. As you could see that as the time, of course, as the time increases, the confidence of the system increases, and in general around 300 to 400 millisecond. So we can get predict the results with very high confidence. However, like initial spikes usually are quite accurate as well, but network requires more time to gain confidence. The average latency was as low as 65 milliseconds on average, with a dynamic power of just with less than 10 milliwatt for the Kapoor-based system. That on top of 5 milliwatt power for the DVS camera. So the whole system would consume less than 15 milliwatt dynamic power. So that's quite low for real-time gesture recognition. Also, we have apart from Slave Auto tools, we have tools for energy benchmarking as well, which is a key interest for us at Lowy. And typically, the networks trained are usually quite small and they don't fill the entire board. As you can see, some of the networks were consuming as low as 6 cores, whereas one chip contains 128 cores. So they don't even fill an entire chip, but in Lowy, we have tools for energy benchmarking, and what we do is we replicate these networks over the chip and over all the chips available. And Slave Auto also has tools to replicate these networks so that we can get, on average, better energy estimates out of the system. In the next talk, Garrick will talk about these energy benchmarking tools available in Lowy in more detail. But that's it from my side.